Welcome to one more video from World's World of Physics. This time I'll be discussing some nuclear processes which are pathways to harnessing nuclear energy for electric power generation. Before we actually come to the nuclear processes proper, let me discuss an introduction to the general principles of electric power generation and then some details of the more commonly used methods for electric power generation. In this context, let us understand what is meant by power generation. It is actually the process of generating electric power from sources of what are known as primary energy. Now, these sources of primary energy are of different types like heat energy, fossil energy, which is derived basically from oil, coal, natural gas, etc. Then solar energy, wind energy, tidal energy, biomass energy, and finally nuclear energy. This is a plot which shows the percentage share of power sources in India. The major chunk comes from thermal energy sources, 66%. The second is, of course, hydroelectric power, which accounts for 20.76% of the total. Then what are known as renewable energy sources, 10.8%. We'll see what are these in the following slides. And then finally, nuclear energy accounts only for 2.56%. We know that electricity is not freely available in nature, so it must be produced or generated. According to the principle of conservation of energy, which is a very strong principle in physics, the total energy of a closed physical system is always conserved. However, it allows for energy transformation from one form to another. That means electricity can be produced or generated by transforming other forms of energy to electricity. In this context, let us just have a glimpse at the units of energy. In the International System of Units, that is SI, the unit of energy is called 1 joule, and it is defined as the work done by a force of 1 Newton when its point of application is moved through 1 meter distance. So the work done W is equal to F into S, where F is the force acting through a distance S. I'll just give one example to illustrate the unit. Suppose we have a mass of approximately 101.94 grams. We tie a string to it and pass the string over the pulley, and then what we do, we just pull and then raise this mass through 1 meter. The energy that we spent in doing this work is actually 1 joule. So that gives us some idea about the magnitude of this particular unit. The commercial unit of electric energy is called a kilowatt hour, and 1 kilowatt hour is equal to 3.6 into 10 raised to 6 joules. Typically, this is the energy consumed by a 100 watts bulb, which is 0.1 kilowatt, glowing for 10 hours. And it is 1 unit of electric energy, as will be recorded in our usual electric energy meter. Production of electricity is carried out in what are called power stations or power plants. Electricity is most often generated at a power plant by electromechanical generators. So there is a principal equipment by means of which we produce electric energy. The fundamental principles of electricity generation were discovered in the 1820s and early 1830s by the British scientist Michael Faraday. His method, which is still being used today, is for electricity to be generated by the movement of a loop of wire between the poles of a magnet. And this is actually the well-known process of electromagnetic induction. And the laws concerning this particular process were enunciated by Michael Faraday himself. So the next 2 slides will illustrate the electromagnetic induction process. So suppose we have a coil of wire wound on some suitable frame and an ammeter is connected to that. So this is kept near, let's say, the north pole of a bar magnet. Now if both the coil and the magnet are stationary, there is no current indicated by the ammeter. Now if we move the magnet towards the coil, then you can see that immediately there is a current induced in the coil. It's in one particular direction, let's say positive current. Now, a similar effect is also observed when the coil is moved instead of the magnet. So we keep both stationary first, there is no current. Then we move the coil towards the north pole. Then also we see that there is a transient current. But now the induced current is in the opposite direction. We can also rotate the magnet or the coil. Then also we will observe a similar induced current flowing in the coil. What we really need is a relative motion between the two, between the coil and the magnet. It can be linear motion or rotational motion. The coil actually cuts the magnetic lines of force produced by the bar magnet. It is seen that the magnitude of the effect will depend on how fast the field lines are cut. In fact, This is the expression for the induced EMF. E is equal to minus N d phi by dt, where phi is the magnetic flux enclosed by each coil and N is the number of turns in the entire coil. So d phi by dt represents the rate of change of the magnetic flux per unit time. And the negative sign indicates that the induced EMF is in an opposite direction to what causes that effect. So this is actually known as Lenz's law. The usual technique to produce electricity is to use what is called an alternator. Now what is an alternator? It is an electrical generator that converts mechanical energy to electrical energy in the form of an alternating current or voltage. Now these are made up of essentially two parts. One is known as a stator and the other is called a rotor. So from the name itself we can understand that the stator will be stationary and the rotor is the one which rotates. The rotor spins inside the alternator and is designed to create a magnetic field. The stator is essentially a box made up of many copper windings wrapped around a hollow iron core. When the rotor spins inside the stator, its magnetic field also will rotate along with that. And this rotation creates an induced electrical current inside the stator's windings. And this current is collected and sent to the power grid. So that is how we generate electricity and then send it to the power grid. So this is a simple example of an alternator with a rotating magnetic core, which is the rotor, and a stationary loop of wire, which is the stator. So the stator coil is connected to a voltmeter so that we can read the voltage induced in the coil. So as the rotor is rotated, current is induced in the stator and the resulting current waveform is what is shown here. Now generally the frequency of the generated voltage waveform is 50 Hz. That means the period of this waveform will be 20 milliseconds. Well, in some places this will be 60 Hz. The following animation illustrates the working principle of an AC alternator. Here we consider the case of a stationary magnet and a moving coil. When the coil is stationary, there is no current in the coil. When the coil is rotated about its axis, an EMF is induced in the coil. Now how is the alternator rotated? This is done by connecting its shaft to what is known as a turbine. It is in the turbine that the conversion from the available primary energy into mechanical rotation is effected and the generator converts its mechanical rotation energy into electric energy. So that is how electric energy is generated. So this is a schematic diagram of the alternator coupled to the turbine. So A is the generator, B is the turbine, 1 is stator, 2 is the rotor, 3 is the turbine blade which is forced to rotate by means of some primary force. Here, of course, the one which I have shown here is moved by means of water. So 4 represents the water flow in this direction so that the blades of the turbine will be moved. And the shaft of the turbine 5 is coupled to the shaft of the alternator. So in the power station we use the alternator to produce the electric power and then some sort of power transformer will be used to boost up the voltage and then it is sent to the grid. And at particular locations there is a step down transformer which converts the high voltage to 220 volts mains and then there are long transmission lines along which this power will be supplied to the residential consumers or industrial consumers or whatever we want. So generation, boosting up, transmission, again stepping down and then finally distribution to the individual users. Now we come to the commonly used energy sources. There are mainly two categories. One is the renewable forms. This can be used again and again and will never run out. The common examples are solar, wind, geothermal, water. The energy source can be of two types in this category, namely hydroelectric and the oceanic tidal source. And the fifth one is biomass. Renewable energy is energy derived from natural sources that are replenished at a higher rate than they are consumed. Sunlight and wind, for example, are such sources that are constantly being replenished and will not run out. The second category is non-renewable forms. These are resources that we can use only once. Examples are coal, oil, natural gas and the nuclear source. Non-renewable energy sources, as I just mentioned, the examples are oil, natural gas and coal. They cannot be easily replaced because they have taken millions of years to form in the first instance. We are using them much faster than they are being made. Hence, one day they will eventually run out. The so-called fossil fuels form the most common energy source. They are nothing but hydrocarbon deposits such as petroleum, coal or natural gas derived from living matter. That is, from the fossilized remains of prehistoric plants and animals that died millions of years ago. So these belong to a previous geologic time, and these are used for fuel. Coal has been extensively used as a source of heat for a long time. As we know, it is a combustible black or brownish black sedimentary rock composed mostly of carbon and hydrocarbons. Coal formation takes a very long time, typically hundreds of millions of years. In fact, that is one reason why it's non-renewable. Oil is derived from petroleum, and we know that petroleum must be first refined to derive oil, gas and other fuels. Natural gas is another fossil fuel formed similarly to oil and found in petroleum. The most common form of natural gas is methane, CH4. Natural gas and oil are both retrieved by the process of drilling from deep underground. Compressed natural gas, that is CNG, and liquefied natural gas, LNG, are other forms of natural gas. A byproduct of natural gas is the so-called propane gas. Burning petroleum products produces immense amounts of air pollution, and these cause smog, leading to human illness, crop failures and acid rain. Uranium is also mined from beneath the Earth's crust, hence it is a non-renewable source because the deposits are limited, and eventually one day all the uranium deposits will run out. Burning these fossil fuels produce excessive amounts of what are known as greenhouse gases. The main example is carbon dioxide. There is also another categorization of the energy resources, namely conventional energy and non-conventional energy. Basically, these are non-renewable and renewable energy sources. This nomenclature comes from the basic nature of these sources. The major difference between conventional sources of energy and non-conventional sources of energy are listed here. This is taken from this particular website. Conventional energy sources are derived from fossil fuels. They are of limited availability, and eventually they will run out, and they lead to high carbon emissions when burned. These are of course non-renewable, but the technology for using these for energy utilization is well established, and the process, the equipment, etc. are relatively cheaper. But we have to depend on what are known as centralized grids for availability of this energy finally to the user. Major environmental impact, and well, connected with this established technology, this is a very mature industry which makes use of the conventional sources of energy. As opposed to this, the non-conventional sources of energy are derived from renewable sources. They are of abundant availability, and the pollution from these will be minimal because of the low or almost zero carbon emissions. Obviously, they are renewable, but it's an evolving technology, and therefore the industries related to this will be just coming up. The initial cost of these establishments utilizing non-conventional energy sources will be pretty high, but in contrast to the centralized grids for the conventional sources, we can have distributed energy systems, and the environmental impact will be minimal because of the low or zero carbon emissions. And as I mentioned, this is just a developing industry. These are the non-conventional sources of energy: solar energy, geothermal energy, wind energy, ocean energy, and hydroelectric energy. Generating renewable energy creates far lower emissions than burning fossil fuels. In fact, transitioning from fossil fuels, which currently account for the lion's share of emissions, to renewable energy is the key to addressing the climate crisis of today. So, I will just briefly discuss the hydraulic power plant which produces hydroelectricity and the thermal power plant. So, we have essentially production of electrical power through the use of the gravitational force of falling or flowing water. It is the most widely used form of renewable energy. So we have a large reservoir of water, and then from this water is released at a controlled rate and falls on the blades of the turbine, thereby rotating the turbine, and this rotation is coupled to the shaft of the generator, where the rotor rotates, rotating the magnetic field, and the stator gets an induced EMF, which is then given to the power lines. So flowing water falling from a height directed at a turbine causes turbine to rotate. The kinetic energy of water is converted into mechanical energy. In turn, this is finally converted into electrical energy via the principle of generation of an electromotive force due to changing magnetic field, or in other words, the electromagnetic induction. Now, what are the benefits of this hydroelectric power generation? Essentially, we don't have to invest on the fuel. The fuel is plentiful in nature. Now, what are the environmental benefits of hydro power? There is no air pollution. There is no operational greenhouse gas emissions, and the savings kilogram of carbon dioxide per megawatt hour of electricity is the following for the various natural sources, and there is no sulfur dioxide or nitrogen oxides. Now, there are also non-environmental benefits such as flood control, irrigation, transportation, fisheries, and so on. Well, disadvantages are the loss of large areas of land under the reservoir, large-scale human displacement, interference with the transport of sediment by the dam, problems associated with the reservoir like climatic and seismic effects, impact on aquatic ecosystems, flora and fauna, etc. Now coming to the thermal power plant. The thermal power station is a power plant in which the prime mover is steam driven. Water is heated, turns into steam and spins at steam turbine, which drives an electrical generator. After it passes through the turbine, the steam is condensed in a condenser and then recycled to where it was heated. The primary heat for generating steam is obtained by burning coal, oil, natural gas, petroleum, naphtha, etc. So these are essentially the non-renewable energy sources. On the plus side, the advantages of thermal power plants are the following. Making energy from thermal power plants is relatively easy as compared to the other types of power plants. The fuel used, namely coal or petroleum oil, is rather cheap. Thermal power plant can be set up anywhere near fuel and water supply, and it requires less space as compared to the hydroelectric power station because of the large areas for which the reservoir has to be maintained. The disadvantages are thermal power plants use fossil fuels to generate electricity, and these fossil fuels causes pollution, and they will be used up very soon. A large water source is required to convert water into steam, and the overall efficiency is not that good, and also the maintenance cost is prohibitively high. So from these one can conclude that a long-term solution to the energy problem is the nuclear energy. Well, the nuclear energy comes from mainly two reactions which are called nuclear fission and nuclear fusion, and we will discuss these in the following slides. Now here in this particular table given a worldwide statistics of nuclear power generation country-wise. So here we have nuclear electricity generation as of 2022 and the operable reactors as of March 2024. As you can see, USA ranks first with a total of 772 terawatt hours of electric power generation, electric energy generation, and the maximum number of reactors operable in the country. India ranks somewhere around the 12th in this list, and the world total consumption of nuclear electricity is 2545 terawatt hours, and there are a total of about 393,873 operable nuclear power reactors. Now, what is the source of nuclear energy? It lies in what is known as the binding energy of the nucleus. In general, the term binding energy characterizes any physical system comprising of a number of individual objects or particles which are bound together via a common force. So the common entity in that system would be a common force. So all the particles are bound together via this common force. Now the system can be as diverse as the following: the solar system, and here the common force is of course gravity. Then we have the atom, where we have the nucleus sitting at the center and the electrons revolving around the nucleus in certain orbits, and here the common force is of course Coulomb force. Next we have the nucleus, where the common force is nuclear force. So we have a system of protons and neutrons which are bound together via the nuclear force. And we have a bigger system like a crystalline objects, and here the bonding is via ionic, covalent or metallic bonding, which are basically electrostatic forces. Now, how do you define the binding energy of a system of bound particles? There are basically two ways in which the definition can be made. The first one is that it is the energy required to separate the system into free individual component particles. Suppose we have the system, bound system available with us, and we want to break up this system into the separated individual particles. So in order to do this, we have to supply an energy which is exactly equal to the binding energy of the system. So unless we provide this energy, the system cannot be broken into the individual separated particles. So essentially this process is what is known as a endothermic process. This is one category of processes, endothermic. That means energy is absorbed in the process from the environment, from outside. The definition can be also made equivalently as the energy released when the separate component particles are combined together to form the composite bound system. So we have the free separated particles which are at a distance from one another, and we want to combine them into the single bound system. So in that process, it is always seen that some amount of energy will be released from the system, and it is essentially the binding energy of the system. So we have energy release from the initial system, so therefore it is known as the exothermic process. Now coming to the nuclear binding itself, nuclei are made up of protons and neutrons, which we refer to as nucleons collectively, but it is found that the mass of a nucleus is always less than the sum of the individual masses of the protons and neutrons which constitute. The difference in the mass is a measure of the nuclear binding energy which holds the nucleus together. Now this binding energy can be mathematically calculated from the Einstein relationship, which is essentially the mass energy equivalence. The nuclear binding energy will be equal to delta m into c squared, where delta m is the mass difference and c is the velocity of light in vacuum. So because of the enormity of the magnitude of c, even a very small amount of mass can lead to a large amount of energy. For example, when a neutron and a proton combine to form a deuteron, a gamma ray is emitted with an energy of 2.23 MeV. Conversely, when this deuteron is bombarded with a gamma ray of energy 2.223 or slightly more energy, the particle will disintegrate. We say that the binding energy of the deuteron is 2.223 MeV, and this is sort of threshold energy for the disintegration of the deuteron to take place. Now this is actually known as photo disintegration. Calculation of the binding energy of the, here this is a simple deuteron system. We have the mass of the proton and that of the neutron, then the combined mass is this much, whereas the mass of the deuteron is only this much. So the difference is equal to 0.002387, and this is exactly equal to the binding energy of the deuteron. So therefore the binding energy essentially arises from the mass deficit. The enormity of the nuclear binding energy can perhaps be better appreciated by comparing it to the binding energy of an electron in an atom. So I have compared the binding energies of a hydrogen atom with that of a alpha particle. So on the atomic side we have 13.6 eV as the binding energy of the ground state of the hydrogen atom, whereas for the alpha particle the binding energy is about 28.3 MeV. So there is a million times difference between the magnitudes of the two types of energy. So you can appreciate the nuclear scale of the binding energy. The two important pathways to harnessing the energy within the nucleus are the two nuclear reactions, fusion and fission, nuclear fission and nuclear fission. So we will briefly discuss these two processes. Firstly, the nuclear fusion is the reaction in which two or more nuclei combine together to form a nucleus of a new element with higher atomic number. That means essentially we start with a certain number of protons in each of the two nuclei. So when we combine this, we get a higher atomic number nucleus because of the more protons in the nucleus. In this particular animation is illustrated the nuclear fusion process. Here we have a projectile moving towards the fixed target. Here the two of them fuse together and produce a compound nucleus. In the process, a beta or a gamma ray may be emitted, and simultaneously energy also will be released in the process. So this is the nuclear fusion process. The simplest case of nuclear fusion is that of two hydrogen nuclei. They combine together to form a deuteron, and in that process an electron will be released, and some total energy will be released by this process. Fusion of two hydrogen nuclei produces a deuterium nucleus. 1H plus 1H gives 2H plus beta. So deuteron plus an electron. This is the next higher scale process. We have a proton and a deuteron. Fusion of a hydrogen nucleus, which is essentially a proton, with deuterium nucleus. So this will produce a tritium nucleus, plus of course a beta part. Now come to the nuclear fission process. Fission may be defined as the process of splitting a heavy atomic nucleus into two or more smaller fission fragments. The fission fragments are generally in the form of smaller atomic nuclei and plus a few neutrons. So in the following animation, we can demonstrate the nuclear fission process. So originally, we have a excited heavy nucleus, and subsequently it splits into two fission fragments, and maybe 1 or 2 or 3 neutrons also will be released, and also at the same time a huge amount of energy will also be released in the process. That is our nuclear fission process. So this is a particular example. Plutonium-239, it fissions into palladium 112 and cadmium 124 plus 3 neutrons. So this is only a particular example of this particular process. There are other pathways in which the nucleus can fission. Now both of the above reactions, namely fusion and fission, cannot proceed naturally under normal conditions. The main reason is the existence of what is known as a potential barrier, which prohibits the occurrence of the system in a natural way. So this is just like a hillock. One has to literally climb over the barrier in order to go from one side to the other. For fusion, this barrier is known as the Coulomb barrier. The occurrence of this Coulomb barrier can be well understood by looking at this particular figure, where I have plotted the potential energy of two protons as a function of the distance between the centers of the two protons. So you can see that at very short distances we have the strong nuclear force which binds the system, and at very large distances essentially we have the Coulomb repulsion between the positive charges on the two protons. And in between you can see that the combination of these two opposite types of forces, namely the attractive nuclear force and the repulsive Coulomb force, results in a barrier like this. So if you have two protons coming from a large distance and then trying to come closer and closer, and then if they try to fuse, then they encounter the Coulomb barrier. So they cannot go beyond this point in a classical fashion. Only if they have sufficient energy above the barrier, then they can go into the bond system. So therefore classically the fusion of two such protons are prohibited. But then there is a quantum mechanical process which is known as tunneling through the barrier. So they don't have to go over the barrier, but they can tunnel through the barrier and go to the bond system. So this is known as quantum mechanical tunneling process. For fission, this is the fission barrier, so-called fission barrier. Here again, the occurrence of the barrier is due to the interplay of the binding due to the nuclear force at short distances and the repulsive forces due to the positive charge. So in between we get a barrier. So this bond system, which is the heavy nucleus, if it wants to go into the separated fission fragments, then it has to cross the barrier. So unless sufficient energy, which is equal to this much energy, is applied to the nucleus cannot fission. But then again, the quantum mechanical tunneling process will come to the rescue. The system can tunnel through the barrier and then undergo the fission process. So this is known as spontaneous fission. But this is very rare. This is a pictorial representation of the tunneling process. So this is the barrier. This is the classical picture. The dog cannot cross the barrier unless it has so much energy and it jumps over the barrier to the other side. So it cannot go after the man. So it is something like this. We have to go around, climb over around and then go to the other side. But then the quantum mechanical picture is that the dog can literally make a tunnel through the barrier and then go to the other side and try to catch the. Similarly, we have here, there is a tunneling possibility to go to the other side. In both the above reactions, namely fusion and fission, we saw that large amounts of energy will be released. The reason is precisely Einstein's mass energy equivalence, E is equal to mc squared. The total mass of the initial system is more than the mass of the final system. The difference in mass appears as kinetic energy of the final system. For example, the fusion of two hydrogen nuclei releases about 0.86 MeV, and the fission of a uranium nucleus releases typically about 200 MeV. Now this is a usual plot one sees in almost all nuclear textbooks. This is actually a plot of the average binding energy per nucleon in units of MeV as a function of the mass number of the nucleus. So you can see that at low mass numbers, the binding energy per nucleon is small. Then as A increases, this quantity increases in magnitude and then gradually increases, and finally around the nuclei near the iron region, iron group, it reaches some sort of a saturation, and thereafter it gradually decreases as we go to heavier and heavier elements. This tells you that the nuclei in the iron group around iron are most tightly bound. In fact, nickel 62 is the most tightly bound nucleus, followed by iron 56. So here both these have about 8.8 MeV per nucleon binding energy. So this figure illustrates that if we combine two light nuclei to form a heavier nucleus, then energy will be released. Similarly, if we fission a heavy nucleus into two average mass nuclei, the fission fragments, then also a certain amount of energy will be released. So therefore, in the next slide, which is essentially the same slide but sort of inverted. So the fusion process goes in this direction and the fission process goes in the opposite direction. But both of these will yield energy. Some amount of energy will be released in the process in either of these two cases. Well, I talked about spontaneous fission, in which an inherently unstable nucleus tries to tunnel through the barrier and go to the other side where we have the fission fragments. So the probability, as I mentioned, is very rare because of the quantum mechanical process being of low probability. On the other hand, one can induce nuclear fission in an otherwise stable nucleus, which does not fission spontaneously. So these nuclei are capable of absorbing a slow neutron, for example, and then undergoing a fission reaction. So these are called a fissile nuclei. One example of a fissile nucleus is uranium-235, plutonium-239. So this will absorb neutrons and then the resulting nucleus will fission into the fission fragments. On the other hand, uranium-238 cannot fission by absorbing a slow neutron. Now these fissile nuclei are generally atoms with more neutrons than protons. The nuclei of such heavy atoms are struck by neutrons, initiating the fission process. And the fission occurs when the strong nuclear force is disrupted by an incoming projectile, for example, a neutron. When the strong nuclear force is disrupted, the electrostatic repulsion splits the nuclei and they are repelled and go away as the fission fragments. So therefore, fission represents a competition between the binding due to the nuclear force and the Coulomb repulsion. We know that binding energy is proportional to A and the Coulomb repulsion is proportional to Z square. So therefore, there is a balance between these two, and when that balance is tilted, fission will occur. Now, if sufficient neutrons are present, we may achieve what is known as a chain reaction. A chain reaction is one in which a particular fissile nucleus absorbs a neutron, then it produces the fission fragments and a few neutrons, and then these neutrons, they induce fission in further uranium nuclei, and thus the process will be repeated. So this is known as a chain reaction. So if free neutrons produced by fission can hit other nuclei, emitting more neutrons, repeating the reaction over and over. A series of fission reactions is called a chain reaction. Now if the chain reaction proceeds at a very fast rate, we have an uncontrolled chain reaction process, and this will release a huge amount of energy in a very short time period. That is exactly what a bomb does. So this will require a critical mass of the starting material to produce more reactions. Now on the other side, we have controlled nuclear fission reaction, which takes place in a nuclear reactor. So we have the initial neutron being absorbed by uranium nucleus, produces fission and then a few neutrons, and exactly one neutron from this will induce fission in another uranium nucleus, and so on. Therefore, this is actually a controlled chain reaction. So this requires only one neutron which is produced per generation can strike another uranium nucleus. When the amount of fissile material is small as compared to the critical mass, many of the neutrons don't strike other nuclei, and therefore the chain reaction will stop. And exactly this is what is known as the critical mass. The amount of fissile material necessary for a chain reaction to become self-sustaining. That is the critical mass of the fuel. In a nuclear reactor, nuclear chain reactions are initiated, controlled and sustained at a steady rate, as opposed to a nuclear bomb in which the chain reaction occurs in a fraction of a second and is uncontrolled and causes an explosion. So a nuclear reactor is a controlled chain reaction device. Here, fission produces large amounts of heat energy, and it is this heat that is captured by the nuclear power plants to produce electricity. So this is a typical schematic of the nuclear power plant. We have the reactor vessel, we have the fuel, uranium for example, and then initially a starting neutron will be released in the system. So that will start the chain reaction, and the heat is produced because of the fission process, large number of fission processes, and then heat is applied to water, which is heated up and converted to steam, and the steam drives the blades of the turbine. In turn, the shaft of the turbine is connected to the shaft of the generator. The rotor rotates inside the stator coils, and that induces the electric current, and then that is distributed to the power grid. So controlling the reactor is done by getting rid of extra neutrons. So how do we do that? We insert what are known as control rods, which are essentially made of cadmium to absorb the extra neutrons, and thereby we achieve the steady state nuclear reaction. Now how do we stop the reactor? So we just insert the control rods. So many neutrons are absorbed. Fewer neutrons means fewer fissions, means less heat. So this can be very fast. That means essentially the full power to shut down will take less than a second. The advantages of nuclear power plants are the following. The nuclear power costs about the same as coal. So it is not expensive to make. Of course the initial cost may be high. They do not produce smoke or carbon dioxide, so it does not contribute to the greenhouse effect. The amount of energy produced is much large compared to the other types of power stations, and the amount of fuel required is extremely small, precisely because of the Einstein's relation E is equal to mc square. The enormity of the magnitude of C tells us that a very small amount of fuel will result in large amount of energy. The waste material produced is small compared to the, for example, the thermal power plants, etc. And the nuclear power is more or less reliable. But these plants are not without disadvantages. Although not much waste is produced, it is very, very dangerous. These are radioactive waste, so they must be sealed up and buried for many thousands of years to allow the radioactivity to die away. The radioactivity is not short-lived, it is long-lived. So therefore we have to bury them underground without ever allowing that to be exposed to the atmosphere. For all that time, it must be kept safe from earthquakes, flooding, terrorists, and anything else. And this is also a difficult process. Although nuclear power is reliable, but a lot of money has to be spent on the safety aspects. If something does go wrong, a nuclear accident can be a major disaster for the whole community. Now coming to the alternate process of nuclear fusion. As we have seen, it is a nuclear reaction whereby two light atomic nuclei fuse or combine to form a single larger nucleus, which is lighter than the sum of the two that fuse. The lost mass, delta M, is converted to energy. E is equal to delta M into C square. In order that fusion occurs, a large amount of energy is needed to overcome the repulsion of the electric charges of the nuclei and fuse them together. So this is essentially concerned with the Coulomb barrier. So this repulsion is called the Coulomb barrier. It is highly unlikely that the two positive nuclei will approach each other closely enough to undergo a fusion reaction unless they have sufficient energy to overcome the Coulomb barrier. So this fact we have already seen. So classically we have to climb over the barrier, so the fusing system must have enough kinetic energy. But of course the nuclei can tunnel through the Coulomb barrier, so even with less energy there is a finite probability that the nuclei can tunnel through the Coulomb barrier and undergo the fusion process. But then the probability will be extremely small. So unless we have sufficiently large number of fusing nuclei, we cannot achieve any appreciable amount of nuclear fusion. So the lightest case of nuclear fusion we have already seen, hydrogen on hydrogen. Similarly, we can have deuteron on deuteron, resulting in alpha particle plus energy, or you can also have deuterium plus tritium, resulting in helium and a neutron. So this also will release large amounts of energy. Now it is obvious that fusion reactions cannot occur naturally on our planet on account of the Coulomb barrier, because the energy of the fusing participants are extremely small. It was the British physicist Arthur Stanley Eddington who first proposed in the 1920s that the sun and the stars were powered by the fusion of hydrogen into helium. So he argued that the source of energy in the sun and the stars is basically the fusion of hydrogen nuclei into helium. Now it is a well-established fact that nuclear fusion is the principal type of process responsible for energy generation in sun and the stars. The large masses of the stars, the high densities and the high temperatures of the stars, these are all factors which provide the appropriate initial conditions needed to fuel the fusion reactions. The sun fuses hydrogen atoms to produce helium, some subatomic particles and vast amounts of energy. So this is a pictorial representation of the basic process which is taking place in the sun for energy production. So the sun, made mostly of hydrogen, produces its energy by the fusion of two hydrogen nuclei. So we start with two hydrogen nuclei, essentially produces helium-3 as a step-by-step process. Then two such wings collaborate to yield finally an alpha particle, helium-4 nucleus, and releases 2 protons. So we start essentially with 4 protons and we get up with a helium nucleus. Therefore, the heat and light that Earth receives comes from this process. About 1% of the Sun's hydrogen has been changed into energy so far. Therefore, we can appreciate the fact that the Sun has enough hydrogen to continue fusion reactions for another 5 billion years. So we are all safe in that regard. Now, what about achieving the fusion process in the laboratory? See, we have to basically have charged nuclei which have to collide and then fuse together. So this is essentially the fuel. Not only collide, but they have to overcome the electrostatic repulsion. Well, either in magnitude or we can rely on the quantum mechanical tunneling process. Anyway, it is necessary that the particles have very high kinetic energy, and this is essentially related to the temperature of the nuclei. Then we also should have heat to heat up the fuel, and also electromagnetic fields to control and confine the resulting plasma. Now, what is a plasma? Plasma is essentially a system comprising of completely stripped atoms and the free electrons. To get an idea of the required temperatures, we can see that the temperature of the Sun's core is about 15 million degrees Celsius, and if you want to convert this to kinetic energy, this corresponds to 12.9 keV. So therefore, if you want sufficient number of fusion processes to take place, the temperature of the participating nuclei should be, the kinetic energy of the participating nuclei should be about around 13 keV, or the temperature should be something like 15 million degrees Celsius. In contrast, at room temperature, the average energy of air molecules is only 0.04 electron volt. So compare this with this. This is electron volts and this is keV. So therefore, we have to heat up the plasma to such a large temperature. This is again showing the same graph. Once again, the Coulomb barrier for the proton-proton system. So the Coulomb barrier is about 0.6 MeV. But then, of course, the possibility of tunneling is the one which helps us in promoting the fusion process as a source of power generation. See, the plasma, which consists of the stripped nuclei and the electrons, have to be confined to a small volume, and the density of the plasma should be high so that enough fusion reactions can take place. So there are basically 3 methods for confining the plasma. Of course, the natural method existing in the universe is the gravitational confinement, which you find in the sun and the stars. So the plasma there is confined to that particular heavenly object basically because of the gravitational forces. Then we have magnetic confinement and inertial confinement. What is magnetic confinement? The magnetic confinement uses magnetic and electric fields to heat and squeeze the hydrogen plasma. How does this work? The plasma is produced by microwaves, electricity, or natural particle beams from accelerators. So this will heat up a stream of hydrogen gas and turns the gas into a plasma. This plasma gets squeezed by superconducting magnets, thereby allowing fusion to occur. Another method is inertial confinement fusion concept. So here, laser beams or laser produced X-rays rapidly heat the surface of the fusion target, forming a surrounding plasma envelope. Then the fuel is compressed by the rocket-like blow-off of the hot surface material. And during the final part of the capsule implosion, the fuel core reaches 20 times the density of lead and ignites at a temperature of 100 million degrees centigrade. This will result in thermonuclear burn-up process. This spreads rapidly through the compressed fuel, yielding many times the input energy. Now the tokamak is the most efficient shape for the magnetically confined plasma, and this is in the form of a donut shape. It is called as toroid, and the reactor of this shape is called a tokamak. This is basically a Russian acronym for toroidal chamber with axial magnetic field. So we have a toroidal chamber and there are magnetic fields of different configurations, and obviously inside we should have a vacuum chamber in which the gas is led, and then it is by supplying sufficient heat, this is converted into a plasma, and then it is maintained in a confined volume by means of magnetic fields. Now, what is the working of a fusion reactor? The fusion reactor will heat a stream of deuterium and tritium fuel to form high temperature plasma. It will squeeze the plasma so that the fusion can take place. The lithium blankets outside the plasma reaction chamber will absorb high energy neutrons from the fusion reaction to make more tritium fuel. The blankets will also get heated by the neutrons. The heat will be transferred by a water cooling loop to heat exchanger to make steam. The steam drives the electrical turbines to produce electricity. The steam will be condensed back into water to absorb more heat from the reactor into the heat exchanger. Now just a diversion here, how are temperature and fusion related? How can we have two nuclei get close enough to combine? They must be moving very fast. All nuclei are positively charged, they repel each other, so the kinetic energy must overcome electric force to push them close enough to combine. The kinetic energy increases, the temperature increases. So temperature must be millions of degrees centigrade like sun and other stars. So this is a typical schematic of a fusion reactor. We have the plasma where the fusion reactions occur. Fast neutrons from fusion reactions heat the blanket, and then this heat is transferred to the fluid. There is a heat exchanger, steam is produced, it runs the turbine runs the generator, and finally we get electric power output. Now these are the advantages of fusion power. Environment friendly as no greenhouse gases are produced. Virtually limitless fuel is available as the stocks are supposed to last for a really long time. Basically it is hydrogen which is available in plenty from water. There is no chain reaction. So there is no chance of major accidents as the reactions can be stopped anytime by just cutting off the supply of the fuel, which is also quite low. The cost of the fuel is very low. This can be used for interstellar space where solar energy is not available. Of course, some problems like freshwater shortages can also be solved because they exist mainly because of the power shortages. Then these are the disadvantages. The technology is still unproven to be 100% efficient, especially at a commercial scale. The initial experiments have been very costly, and as of now, the energy required to initiate the fusion process is greater than what is generated. So the overall efficiency is very low. The materials for the entire setup has to be worked upon so that it can take the excessive temperatures produced during the process, so that they have to withstand the temperature without melting. So some special materials will have to be generated, and of course the heat transfer to these materials should be to the minimum, thus preventing them from melting. Now the ITER or International Thermonuclear Experimental Reactor. This is an international nuclear fusion research and engineering mega project which would be the world's largest magnetic confinement plasma physics experiment. This is an experimental reactor. It's a research project established in October 2007. Currently the world's largest and most advanced experimental Tokamak nuclear fusion reactor, and its headquarters is in France. The ITER project aims to make the long-awaited transition from theoretical studies of plasma physics to full-scale electricity producing fusion power plants. So that means essentially coming to reality, real use of the nuclear fusion power plant. So that is what the ITER aims at. The project is funded and run by its member entities, which include the European Union, India, Japan, China, Russia, South Korea and the United States, among other countries. In India itself, we have a very advanced Tokamak system, which is known as the Aditya Tokamak at the Institute of Plasma Research, Ahmedabad. It's a nuclear fusion research equipment for studies on magnetic confinement of plasma, and this is also part of the ITER program. In China, which is also a participating country in the ITER project, they have a very sophisticated Tokamak coming up. It's already come, and many experiments are being conducted there. It is the EAST, Experimental Advanced Superconducting Tokamak. It's in China under the Chinese Academy of Sciences. Here, a long pulse high parameter plasma operation lasting for 1056 seconds was realized. In fact, this is the longest time for which the plasma could be maintained so far. And this has created a new world record for the operation of the Tokamak experimental device. In 2021, the East had maintained a temperature of 158 million degrees Fahrenheit. That means 70 million degrees Celsius for 1056 seconds. That's what I just mentioned, according to the Xinhua news agency. The achievement brings scientists a small yet significant step closer to the creation of a source of near unlimited and clean energy. In April 2023, this Tokamak, which was nicknamed Artificial Sun, had broken all records as it generated extremely hot plasma for 7 minutes. China, like India, is a member of the ITER consortium, and the East is a testbed for the ITER technologies. Now, before concluding, I will just pose a $1 million question of the decade, namely, when will a commercial power generator using nuclear fusion become a reality? I know that this question will be in your minds. Most of you will be just pondering on this. As of now, it is very difficult for anybody to answer correctly this particular question because of the technological difficulties and sophistications involved. Now, there was a joke some time ago about the fusion energy is that it's 30 years away and it always will be. So essentially it's saying that it can never be realized. But I don't think that is the case now, because technology has advanced so much that the future may be very much in sight. The significant recent advances in fusion science and technology could potentially put the first fusion power on the grid as soon as the early 2040s or 50s. When British physicist Stanley Eddington first proposed in the 1920s that the sun and stars were powered by the fusion of hydrogen and helium, his idea sparked a rush of research and speculation into the possibility of bringing this energy source to Earth. It was not long before journalists and fiction authors were predicting a time, surely not far away, when the world would be powered by simple fusion reactors requiring nothing more than abundant hydrogen from water. Well, let's all hope for the best. I will end this video at this point. If you like this video, kindly click on the like button and share with your friends and relatives, and also with your different groups. If you have not already subscribed to my channel Murali's World of Physics, kindly do it now. And please don't forget to click on the bell icon so that you will receive notifications in future about my upcoming videos. I'll be back soon with yet another video on basic principles in physics. Till then, goodbye.